Welcome to Lecture 7. Today we will focus on the reactivity of substituted benzenes in electrophilic substitutions and furthermore on the synthesis of substituted benzenes. Before we start, we will shortly revise the last lecture. In the last lecture, we focused on the electrophilic substitution of benzene, and we learned that there are 5 important electrophilic substitution reactions of benzene, namely halogenation, nitration, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylations. Very general, in an electrophilic substitution reaction, benzene acts as nucleophile and therefore attacks in the first step an electrophilic site. Hereby, a non-aromatic carbocation is formed. And then subsequently in the second and faster step, this non-aromatic carbocation gets deprotonated and we end up with the substituted benzene. And the driving force for the second and faster step is the regeneration of the aromaticity of the benzene ring. Hence, in an electrophilic substitution reaction of benzene, the hydrogen atom on the ring is replaced by an atom or a group. And here on the right side, we can see an overview of the formed coordination complexes for the 5 important electrophilic substitution reactions of benzene. So for the halogenation, the coordination complex results from the reaction of the halogen molecule with a Lewis acid, and this coordination complex is a stronger electrophile than the halogen molecule. For the nitration, this nitronium ion, which is a strong electrophile, results from an acid-base reaction of sulfuric acid and nitric acid. For the sulfonation, the initial step is again an acid-base reaction in order to form a stronger electrophile. And here the sulfuric acid reacts with sulfur trioxide, and this hydrated sulfur trioxide reacts then as electrophile. In the Friedel-Crafts alkylation, the primary halogenoalkane reacts with the Lewis acid to form a more electrophilic coordination complex, which is shown here. Similar to the Friedel-Crafts alkylation, in the Friedel-Crafts acylation, the acyl chloride reacts with the Lewis acid catalyst to form this coordination complex. However, this coordination complex is not stable, so it will directly break down to form an acylium ion and tetrachloroaluminate. And the positively charged acylium ion is stabilized by resonance and a stronger electrophile than the acyl chloride. Hence, the acylium ion will react with benzene. If we now have a closer look on Friedel-Crafts reactions, so on Friedel-Crafts acylations and Friedel-Crafts alkylations. Important to know is that Friedel-Crafts alkylations generally yield multiple products, particularly when using primary halogenoalkanes. And there are 2 reasons for the multiple products. So first of all, there is a possible rearrangement of the intermediate coordination complex. And then second, polyalkylations take place. And hence, as you can see here, if we have a reaction of benzene with 1 bromobutane and Lewis acid, then we will not only end up with 1 butylbenzene, but also with 1 sec-butylbenzene and 1 4-dibutylbenzene. And additionally, other substituted benzenes are also formed. And therefore, Friedel-Crafts acylations are more useful in synthetic reaction than Friedel-Crafts alkylations, as they don't yield mixtures of multiple alkylated benzenes. So, for the formation of alkyl benzenes, usually Friedel-Crafts acylations are the first step. Then in a second step, the produced acyl benzene can be converted with a reducing agent that converts the carbon-oxygen double bond into a methylene group. And commonly, for this step, the Clemmensen reduction is applied. So if we want to produce 1 butylbenzene, we start with a Friedel-Crafts acylation, followed by a Clemmensen reduction, where we have an acidic solution of zinc dissolved in mercury. And then we end up with only 1 butylbenzene. So now we know how to introduce a substituent to the benzene ring, but how do substituted benzenes react in electrophilic substitution reactions? And therefore, it is important to consider two different things. First, we need to consider the effect of the substituent on the rate of the further electrophilic substitution. And second, the position of the further substitution. An electrophilic substitution, the slower step, is the formation of the intermediate carbocation by the reaction of benzene with an electrophile. And the lower the energy of the transition state, which leads to the carbocation, the lower the activation energy and the faster the rate of the electrophilic substitution. And to predict the effect of a substituent on the rate of further electrophilic substitutions, you need to consider whether the substituent stabilizes or destabilizes the transition state, which leads then to the carbocation. And let's have a look on the very general reaction mechanism. So we have a substituted benzene with a substituent called R. And then the reaction with an electrophile leads to this transition state, and then the formed carbocation is resonance stabilized. In general, substituents that stabilize the carbocation make the ring more reactive to electrophilic substitutions than the benzene, and therefore these substituents are called activating groups. Conversely, substituents that destabilize the carbocation make the ring less reactive to electrophilic substitutions than benzene and are therefore called deactivating groups.